welcome back to lecture number 36. Myself Dr. Sachindra Kumar Rao, Department of Mechanical Engineering, C.V. Raman Global University, Bhubaneswar. Last class we have discussed first law of thermodynamics for closed system, and we have discussed also the term enthalpy and internal energy and also specific case. And this class we are going to discuss the first law of thermodynamics for a open system. Open system, that means the system where there is a fluid flowing and also some amount of fluid is leaving. And for closed system we have only considering the heat transfer and work transfer for a closed system only, and other form of energy cannot transfer to the system or from the system. But in this system, in the closed system, we will define a control volume where a mass entering and one mass is leaving. So the learning outcome for this class, for this lecture is first law of thermodynamics for open system. Then we will derive a steady flow energy equation, and lastly we will see a perpetual motion machine kind 1. Okay, so now this diagram, it is a system where you can see this is a system where mass entering, a fluid is entering here and a fluid is leaving here. The mass entering M1, the section 1 and section 2 where mass entering, and section 2 mass is leaving, and one form of energy, that means in the form of energy heat, it is entering into the system, and we can define in the form of rate, as it is a flow process, so we can define in the rate term. Similarly also, as a output, there is a work output is from the system, that means some amount of work performed by the system. So now there are two form of energy due to the inlet of fluid flow, and another is heat transfer to the system, and there is a mass leaving from the system due to which some amount of energy leaving, and there is a work is output from the system, and it is having a some height from the datum line. Okay, now we will take an assumption that at inlet and outlet both the section, the property are not changing, it is invariant. So property of the fluid is not changing. So now we derive an expression for conservation of energy, conservation of mass. That means what is the amount of mass accumulating here, that means we can say the mass entering here, let's say dm1 in the section 1 with respect to time, the rate of mass entering it section 1. Here the mass leaving from the system, let's say dm2 with respect to time. Okay, so as it is a mass conservation, and we can define a mass is there, that is mcv. The mass inside the system is, we define a mcv. Now we can write down the expression like the mass entering, this is the term amount of mass entering to the system, this is the term mass leaving to the system, and this is the net rate change of mass inside the system. So this is the conservation of mass. Okay, so now we will move to the next expression, conservation of energy. So we can see that the energy entering to the system, due to there are two forms. One is due to the flow, due to the energy associated with the fluid, and another form of energy, that is the heat entering to the system. Then we can say what is the amount of energy entering to the system. We can define a term, let's say E is the mass, is the amount of energy flowing through the or going into the system with the fluid. And what are the forms of energy? We can define as E is equal internal energy or intermechanical energy, then kinetic energy, then potential energy, and one more energy, that is flow energy, you can say PV. So these are the form of energy which is moving into the system along with the fluid. Now we can define like this: the mass, the energy, and along with the inlet fluid, that means E1, it is the, if we say E1, all terms will be defined as E1, that means it is at the inlet section. Similarly, the heat entering into the system, del Q by del T, So these are the two terms which are entering into the system. Now in the exist section you will find the amount of energy leaving, that means E2 along with the fluid, that means dma2 by d2, and the amount of work done by the system, that means these are the two work, these are the energy leaving from the system. So now we will accumulate all this term and it will give, if the ECB is the total energy inside the system, then we can say the energy entering into the system and energy leaving from the system, and there will be, it will give you the net rate change of energy of the control volume, because we are defining the control volume of the system as it is a flow system. So we have defined already, this is our control volume, the dotted line showing the control volume. Then so this expression is known as the first law of thermodynamics for a open system. We can say this is the conservation of a mass for open system for a first law, and this is the conservation energy for a open system, and it is known as first law of thermodynamics for open system. Now all these forms are in the form, all these expressions are presented in the form of rate. With respect to time, it is changing. If you consider it as a steady state, then with respect to time, the properties are invariant. That means the inlet property and outlet property all remains unchanged. So what we will get, the rate term, the term dmcb by dt, it will become 0. That means with respect to time, there will be no change of mass inside the system. Similarly, if you consider the energy term, this term also not changing. That means with respect to time, the energy inside the system is not changing. So we can write down dmcb dt equal to 0 for steady state. Similar manner, dcb, that means energy inside the control volume also not changing for the control volume. So now with this expression we will move a steady flow energy equation. Now we will derive steady flow energy equation for a control volume. So now what will become? So as we have seen, dm by dt equal to 0. So now it will become whatever the energy mass entering into the system, that will equal to mass leaving from the system if it is a condition of steady state. Similar manner, for the energy equation, the dECB by dt, it will become 0. So now our expression become dm1 dt, that means energy entering with the inflow and energy leaving outflow, the heat entering into the system and work done by the system. So that will become 0. Now in other form, we are taking dm1 by dt divide in both sides. What we will get? E1 minus E2 plus dq by dm, del q by del m minus del w by del m equal to 0. So another way we can write down del q by del m minus del w by del m is equal to E2 minus E1. So what is E2 E1? Already I have defined is E2, we can write down E is equal to internal energy plus flow energy Pb, then kinetic energy, then potential energy. So we can also write down here E2 is equal to U2, because it is the internal energy at the exit, means section 2, and this is similarly P2 V2, and it is kinetic energy V2 square by 2, and this is the potential energy at the exit. Similar manner, also we can write the expression at the inlet section. That means for E1 this much and E2 this much, because it is in the per unit mass it is written. So now the expression can be written like this: del q by del m minus del w by del m, or if you simplify it, H2. So U2 P2 V2 is the S2 and U1 P1 V1 is the H1. The enthalpy, the expression last class I have also explained, H is equal to U plus PV. So that is replace this, that enthalpy is replacing this internal energy plus PV. So now we can write down del q by del m minus del w by del m is equal to S2 plus V2 square by 2, that means kinetic energy, this is potential energy, this is the enthalpy, minus H1, that means enthalpy at the inlet, plus kinetic energy at inlet plus potential energy at inlet. So this is simply known as steady flow energy equation, and it is very important equations which is used for a particularly open system. Now we will go or analyzes few examples where steady flow energy equations is used to solve problems. So before that, we have some special case, let's say case 1, where the kinetic energy and potential energy are very small. Then the previous expression, if you go back to the previous expression, I am clearing erasing all the information. Now the expression, this is the final expression, steady flow energy equation. Now this term del q by del m, the potential energy and kinetic energy become 0. Then the expression become, so these are this term and this term become 0, and this term and this term become 0. So what we will get? We will get del q by del m minus del w by del m is equal to h2 minus h1. This is for the case where kinetic energy and potential energy are negligible. Then case 2, where only war interaction device, that means the heat transfer del q by del m, this term becomes 0. If this term becomes 0, then what will be our next expression? It will become del w by del m is equal to S1, that means war interaction will be enthalpy difference between inlet and outlet. Then for the case where only heat interaction is there, that means this work interaction, the output is 0. So what we will get? The expression we are going to get it del q by del m is equal to h2 minus h1. Here we have a term h1 minus h2. What is h1? Enthalpy at inlet minus enthalpy at outlet. But here heat transfer is equal to enthalpy at outlet minus enthalpy at inlet. So these are some special cases. And the lastly, for adiabatic cases, for a nozzle, we will going to discuss more elaborately. But still, nozzle, what we will get? For the nozzle, we will get the expression will more elaborately discuss here. So for nozzle, you can see there is a amount of mass entering here, and there is a mass leaving here. So we are having the expression steady flow energy. This is the steady flow energy equation. For the nozzle, what will happen? We can remove this as we are considering it is adiabatic case. Now this heat transfer becomes 0, and also there is no work done transfer involved, and also due to there is no change in position, that means potential energy becomes 0. There is no change in potential energy. And also if we considering, so it is written there, that means del q by del m 0, del w by del m 0, and the potential energy is 0. Now the expression become h1 b1 square by 2 is equal to h2 plus b2 square by 2. If the inlet velocity, that means v1 is very small, then the expression become h1 is equal to h2 plus b2 square by 2, or v2 is equal to root over of 2 h1 minus h2. So velocity at the exit can be calculated using this formula. So this steady flow energy equation can be used to calculate the velocity. If the inlet velocity is known to a nozzle, then we can find out the velocity at exit of the nozzle. Then another important device, throttling device, where there is a valve, where we can see there is a velocity is here, there is inlet velocity here v1 and exit velocity v2, and we are going to derive the steady flow energy equation, or simplify the steady flow energy equation. So we are having the steady flow energy equation here already we have derived. So here you can see, you can consider this is adiabatic process, and there will be no work transfer involved here. There is no interaction, no heat interaction. So remaining terms are there, and we can neglect the potential energy. So that means this term becomes 0 and this term becomes 0, and the steady flow energy equation now reduced to h2 plus b2 square by 2 is equal to h1 plus b1 square by 2. So if we are considering the velocity are negligible, in many cases we are getting this v1 and v2 are negligible, then what we will get the expression? We will get H1 minus H1 is equal to the H2. That means for a throttling process, the enthalpy are remain constant. So this is a very important question. So it is derived from the steady flow energy equation. The turbine and compressor. So in turbine and compressor, both the cases, in turbine we are getting a work as output, but in the and the case of compressor we are consuming some amount of work and getting some output in the form of heat or other form, but we are getting some amount of work involvement in this process. So let's go to the diagram. Here the turbine is there and it is insulated, and there is some amount of work involved here. There is a work output, work producing device is turbine. So now we can write down this steady flow energy equation. So here this term will become 0 because this heat transfer involvement is, there is no heat interaction to the surrounding. So that means that term is there, but the work output is there. So we can write down, or we can simplify this equation to H1 is equal to H2 plus work term will be there, because we are considering the negligible kinetic energy and negligible potential energy. So that's why the enthalpy term will be there. The two inlet and outlet enthalpy term will be there, and work interaction will be there. So that means H1 will become H1 is equal to H2 plus del W1 by del M. Or we can write down W by M is equal to H1 minus H2. So this is the enthalpy. The work transfer is equal to enthalpy at inlet minus enthalpy at exit. So this is for the turbine, and we can also write down the expression for compressor. It will become W is equal to H2 minus H1. So now another device, that is heat exchanger. So heat exchanger is generally used to transfer heat between two fluids. So you can see that it is a condenser where cooling water is entering in one path, whereas steam is entering another path. So there is an intermediate device is the heat exchanger, where heat is exchanging between this cooling water and the steam, and some amount of condensation water will getting here. So now we have to derive an expression for this heat exchanger. As there are two fluids involved, that means there are many means four temperatures are there. This is T1, we can say this is T2, this is T3, and this is T4. So previously we have seen there are two, one inlet and one outlet, but here there are two fluids, so two inlet conditions, two outlet conditions. Now we can write down, if you simplifying, because there is no work involved here, and though no external heat is entering to the system, that means we are assuming there are no heat transfer involved in the system. So we will also neglect this potential energy, and kinetic energy also we can neglect. Then this expression which go, this is the mass flow rate involved in the cooling water, and H1 is the enthalpy entering here. Similarly, this is the mass flow rate of the steam and enthalpy entering. Similarly, this is the mass flow rate of the cooling water and the exit temperature of the exit enthalpy of the cooling water, and Ws also mass flow rate of the steam, and S4 is the enthalpy at the exit of the steam. So in this manner we can use the steady flow energy equation to solve a heat transfer in a heat exchanger. So these are few devices which can be used using the steady flow energy equation. We can solve these problems involving these devices. And lastly, the first law of thermodynamics, we are going to discuss a perpetual motion machine kind 1. The first law of energy, in the first section I have explained that it is nothing but it is the conservation of energy. That means one form of energy converted to another form of energy. So what is a perpetual motion machine? So it states that that means in a system, if you are transferring heat, it cannot be converted to all form of work. That means if there other than any other form of work, we cannot convert that Q to W. So in a different manner, we can say no machine which would continuously supply mechanical work without some other form of energy this happening simultaneously. Such a function or such a fictitious machine is called a perpetual motion machine kind 1. That means the machine which violates the first law of thermodynamics, that is known as perpetual motion machine of kind 1. So PMM1 is it is a impossible. That means this type of machine really practically not exist. So with this, in a summary, we have discussed a open system thermodynamics, first law of thermodynamics for a open system. Then we have discussed or derived a steady flow energy equation. Then we discussed about PMM1. Then we have discussed the then we will next class we will discuss the limitation of first law, then heat engine, then thermal energy reservoir. So with this, if you for reference, you can use this NPTEL video, and if you have any query, you can contact with this number. Thank you.